Yes, this is a quick episode of the HVAC School podcast. We call them our short episodes. And as always, this episode of this podcast is made possible because of our generous partners, Carrier, Mitsubishi Comfort, and RectorSeal. And all three of them make great products. RectorSeal is a company that you may not know by the name RectorSeal, but you certainly know a lot of their products. I've talked about the Safety Switch, AquaGuard, True Blue Thread Sealant, the ProFit flaring kit that I've talked about a lot. It goes onto the end of a drill that you can use to flare, and also they have a swedging kit. They have a lot of different products, and you can find out more about RectorSeal by going to rectorseal.com. But today we're going to talk about one of the most under-considered and overlooked things that every technician should be looking at when they're doing a commissioning on a system, as well as a repair on a system, especially a repair that includes the air side of the system. And that is looking up the fan charts, the factory expanded performance data on an air handler, fan coil, furnace, whatever you happen to have there. So let's say you've got a piece of equipment. It's a gas furnace. It's got a PSC motor, so just a typical multi-speed motor. There's still some furnaces coming off the production floor of many manufacturers that have multi-speed motors, and you just leave it set on the factory setting. Or a lot of you do. I know because I've worked on a lot of these systems, and they're just set up the way they came from the factory. Or some of you set your fan speed on cool to one tap, and you set your heat to another because that's what you've been told to do. But the question remains, how do you know how to set up the fan speeds? How do you know how to set up a particular air handler for a particular application? And the answer is that you don't unless you look at the fan charts. And so let's talk about this quickly. So first thing is you have to know what the design is of the equipment. Are you designing the equipment to remove maximum sensible, which means maximum capacity generally, maximum capability for dropping the thermostat on the wall? So when you have a system that's removing more sensible heat, that means that, and we're talking about in cooling mode here, that means that it's going to drop the thermostat quickly. It's going to have high capacity. Well, in those cases, you want higher airflow levels. And so typical nominal conditions we talk about in terms of CFM per ton. We'll say, 400 CFM per ton is the nominal setting that you want to set up. And so if you pull out your manufacturer's expanded performance data and you look across, you can see how much airflow you're putting out based on how many BTUs you're putting out. But what you'll find very quickly is that equipment doesn't always put out what we think it should. So just because something says 36,000 BTUs doesn't mean that it's going to put out 3 tons of capacity, and certainly not 3 tons of sensible capacity, because a portion of that is sensible and a portion of that is latent. Latent means the amount of heat energy that goes towards taking that vapor water in the air and turning it into liquid water on the coil and then in the drain pan that runs outside. So when you take heat energy and you put it towards the latent side, that's for removal of moisture. When you have higher airflow per BTU, that equals more sensible. And when you have lower airflow per BTU, that equals more latent. But it also depends on the conditions, because if the conditions inside the space don't have much latent, well, then there's not going to be much latent removal. There's not going to be much latent capacity regardless of the fan speed. And so you're going to be running a colder coil, but that doesn't necessarily impact latent if you don't have a lot of moisture in the air. So if you're running in what rubber meets the road, if you're running in a place like Colorado where it's very dry and very high in altitude, the air has less density to begin with, then you generally run higher air speeds in order to get the same amount of pounds of air over that coil. And you don't care about dehumidification. In fact, you don't want to dehumidify, so you run higher fan speeds and higher CFM per ton. Or a better way to say it is higher CFM per BTU. The CFM per BTU ratio is higher. A more accurate way of thinking about it, rather than saying CFM per ton, would be to say CFM, or how many BTUs are there per CFM. And so in general, that would be 1 CFM per 30 BTUs would be 400 CFM per ton. That's another way of looking at it. And so when you change that ratio, when you have fewer BTUs per CFM, that's an indication that you have higher airflow because you have fewer of the heat units to every CFM of air. That's another way of thinking about it. But however you want to come to the conclusion, in general, we're saying 400 CFM per ton is the nominal, but you can definitely go higher than that if you want to remove more sensible, less latent, lower than that if you want more latent, less sensible. If you really want to know what it should be set to, whenever the design was done for this particular system, they should have done a manual J, which that manual J will show you how much latent and sensible capacity you have during different seasons, generally peak, but you can also look at it during different times of the day, different seasons, and you can calculate how many BTUs you need, both sensible and latent on the cooling side. And so that can help you set up, if you see, all right, we have greater sensible than latent, then you have higher airflow, greater latent than sensible, then you have lower airflow. And generally you're setting it up for, a design day is what they call it. But when you have a system that has some controls in it where it can change the airflow based on high humidity events or low humidity events, it can adjust the airflow, then you also can have some control over that. But in general, you need to at least be able to look at that fan chart and say, all right, what tap am I supposed to put this to in cooling in order to produce the correct amount of CFM for the amount of capacity that I have here? And the truth is that it generally, even on a nominal situation where you have normal conditions, often needs to be less than 400 CFM per ton, because generally, just because you have a 3-ton unit doesn't mean you have 36,000 BTUs. You could have 34,000 BTUs, and so that means you need to reduce accordingly your CFM in order to even keep that ratio. That ratio, like I mentioned, 30 BTUs per CFM. So, how do you set up your taps? We're still there. If you have a PSC motor, you have to look at how much airflow do I need in heating, and that's based on your temperature rise. So you have to calculate. You have to look at that. So generally, you just set it up the way that the furnace comes, and you'd measure your temperature rise, and you'd see am I in the middle of that zone, which is generally about where you want to be. You don't want to be too far high in the zone or too far low in the zone. Too far low in the zone is going to equal poor comfort. Too far high in the zone of your temperature rise in your furnace could equal possibly going out on overload if you got a dirty filter. So you got to set your heating airflow, and then you got to turn around and you got to set your cooling airflow, and your cooling airflow is based on what I just talked about. Setting it up for design day, latent sensible capacity, making sure you kind of get that balance, and all of that information is going to be available from the manufacturer of that piece of equipment. You're going to be able to find all of it. You're going to be able to find what the latent and sensible is based on the outdoor conditions. You can match those outdoor conditions to the design day conditions that you have in your manual J, and you can come up with a very good match. And a lot of people would say, well, this needs to be done by the designer. But the fact is that it's the service technician or the installer who does the commissioning on the piece of equipment and ensures that it's set up properly. The big question becomes, how do you set the airflow? So how do you know how much airflow you're producing? Well, that's where you look at those fan tables from that equipment and you measure your static pressure, your total external static across that piece of equipment. So the static pressure of the return side coming into the appliance, whatever came in the box. So if that's the gas furnace, it's going to be above the filter generally and below the furnace. And then you have the supply static pressure, which is going to be in between the furnace and the case coil. If it's a fan coil, what comes in the box is a coil, blower, in some cases even an air filter. But then you have to do calculations to figure out, additional resistance added by heat strips, added by a filter that's different than the factory filter, whatever the case may be. And the manufacturer is going to give you all this if you read their specifications. You read the total external static, and then you can set the fan speed accordingly. Now, some people don't like this model because for good reasons. Although I think this model is very good for commissioning, and I'm doing testing on this model, it's still not you're still trusting what the manufacturer is saying. And so some people would say you need to measure it by doing a duct traverse or using something like a true flow grid, or some people use an airflow hood. And there's other ways you can do it. Some people use the temperature rise method. But it still comes down to you still need to pull out the manufacturer's information. That's the point of this episode here, this quick episode, is that you've got to look at that manufacturer's information at minimum on the blower charts in order to know how you should set it up. This is all in the commissioning side. If you come to a system that has a non-factory blower motor in it, well, now all bets are off. I mean, the non-factory blower motors, they're set up generally based on the horsepower and the different ranges, that they're all pretty typical, but it's not necessarily going to be exactly the same. Obviously, if you have some gunk buildup in your blower wheel, you got to get that off. Otherwise, your measurements aren't going to be correct. At that point, you pretty much are stuck with doing a true measurement of some sort, using a true flow grid, doing a duct traverse, maybe using the temperature rise method, although that method is also subject to quite a bit of inaccuracies. We're going to cover that on another podcast, how to actually do the sensible heat equation in order to calculate airflow based on temperature rise. But ultimately, you still have to be responsible for setting it up so that way it produces the correct amount of airflow in both heating and cooling. Main point being, you can't set something up for heating and assume that it's right for cooling. You can't set something up for cooling and assume that it's right for heating, especially when you have a gas appliance, because in that circumstance, you have two totally different sources of heating and cooling. And when you have two totally different sources of heating and cooling, you've got a gas furnace that could be 70,000 BTUs, and you've got an air conditioner that could be 36,000 BTUs, and they have different criteria for how much temperature rise is desirable. You can't assume that one is going to be correct with the other, especially in circumstances where you have a vastly oversized furnace, so where the furnace is much larger than the air conditioner. That can cause some real challenges. And in some cases, it's very difficult to get the airflow perfectly correct. But as a service technician in the field, you've got to be able to reference back to that manufacturer's information, and you've got to know some ways of measuring airflow if you don't have the manufacturer's information or if you have a non-standard blower device. So if let's say you're going to a system and you're replacing a X13 motor or a factory motor with a new Evergreen motor, or Toad Line makes one called the Flex motor. That motor is a constant torque motor, but it isn't calibrated for airflow. So for example, you look at the specs on that motor, it's going to tell you, here's the horsepower, here's the different speeds, but how much airflow those speeds produce, they're going to be constant, relatively constant, up to about 0.9 inches of static. They're going to be relatively constant, but you still don't know what it's going to produce unless you measure that airflow. And so you've got to have a way of measuring that airflow, of which there are many different ways you can do it, but you've got to know the ways that exist in order to set it up properly. Otherwise, you really are totally guessing. If you take a Flex or a Evergreen motor and you're replacing an X13 or a factory motor, you really have no way of knowing what that is, unless it's the type of motor that you can set up to match a factory motor, some sort of program it. There are some options for programming a motor module or an aftermarket motor to original manufacturer specifications. But unless you know how to A, read the manufacturer's charts, B, measure airflow, you're not going to be able to set things up properly. If you're commissioning a new piece of equipment, then you don't necessarily need to measure now, I know this is heresy to some of you, but this is baby steps, right? Measuring the airflow isn't as important so long as the manufacturer's charts are correct, because you've got a new piece of equipment, it's clean, it's out of the box, you can measure the total external static, and you can have a much more accurate measurement. But later on, once that thing gets dirty and maybe somebody has messed with it and made some changes to it, maybe it doesn't have a factory motor, at that point, being able to measure that airflow in the field becomes absolutely pertinent. So you have to have some way of accomplishing that, of which there are many, and Bill Spone and I talk about that in the last podcast. But being able to read fan charts, looking up fan charts regularly, that should be a regular thing. If you go a week and you're not looking up manufacturer specs on at least 10 systems, you're probably not doing your job right, frankly. And I know a lot of you aren't doing that, which is why I'm encouraging you here. It's sort of like early on when people started talking about removing cores and using big hoses on evacuation, people are like, I don't need to do that. But what I'm telling you, in testing equipment and in commissioning equipment, referencing the charts, knowing how to use a manometer and check static pressure are the basics. I mean, that's just the bare basics when it comes to measuring airflow. And then from there, you learn the additional skills of, doing a duct reverse, doing the temperature rise calculation, measuring a static pressure drop across an evaporator coil. Because in some cases, you're almost going to be using a couple different measurements and averaging them in order to come up with the truth, because measuring airflow is very hard, like we're going to talk about more and more as we move forward in the podcast. Hopefully that helps, and I hope you have a great day working out there in the field, and we will talk to you next time on the HVAC School Podcast.